So, good morning. So I will talk about k-means clustering with Hölder divergence. So this is a work whose main contributor is Frank Nielsen from École Polytechnique in Paris, done with a former PhD student of mine who is now in Saudi Arabia, will move to Australia very soon, and I'm from University of Geneva in Switzerland. So the outline of the talk is basically, the talk is basically about divergences, which is, as was said in the previous talk, measures about between probability density functions or positive functions. So basically, I'll go on explaining how you can construct a principle to construct divergences with some property, essentially being a pseudo divergence or being proper divergence, and then go on with the construction of divergences based on the Hölder principle, and then apply it for clustering, because the idea of having a divergence is to have some form of a distance measurement, and then when you have this, you can perform clustering of probability density functions. So basically, the general principle for constructing divergences is that if you start from an inequality that you know, with the left-hand side and the right-hand side, provided that the left-hand side is positive, so left-hand side involving two functions, then you can create a divergence by simply measuring the tightness of this inequality, basically whenever it becomes like equality or not. And with this constraint, basically you end up with a divergence which has the property, weaker properties than the distance, which is the fact of being positive, being proper if only this divergence function is 0 whenever the two members are equal. Otherwise, it's said to be improper, and to be projective whenever you have that kind of relationship, meaning that you can actually scale every of the members. And this property will actually be reflected in the construction. So basically, we can apply this principle on inequalities, and one famous inequality is Hölder inequality, which essentially says that when you have two measurable, so here it's added positive so that we can get rid of the absolute values. So you have positive measurable real-valued functions p and q on the same support, that's it, so you can superimpose them. Then the Hölder inequality says that the norm 1 of this product is actually less than the product of their respective norms with indices both positive and being related by this exponent conjugacy. So basically, these can be summed up in one by just computing one after the other. And then, since you have this, you have one particular case of the Hölder inequality applied to integration, which is to these integrative norms, which is like this, with an equality if and only if the two functions are linearly dependent, which is that relationship, right? So basically, we use that generic inequality, which we map in that very specific case, and we use this to construct the divergence. So using the divergence construction principle with the Hölder inequality, you can end up with a Hölder divergence, which in that case is a pseudo-divergence because it's not proper, with parameters alpha, which somehow includes the beta, because the beta and alpha are exponential exponent conjugate, and extra parameters that enable the scaling. So for specific positive measurable functions and whose exponent can be integrated. So basically, this Hölder divergence taken as raw from the inequality is a pseudo-divergence because there's no triangular inequality and there's no law indiscernible, meaning that it's not proper as a divergence. But since we know that this is equal under some condition, we can actually instantiate that condition on the exponent to merge them and to relate them and create a proper Hölder divergence under that form, with relating basically the indices before by one relationship, which means that basically we end up with a proper divergence, which means that this will sort of compact the inequality in a fact of making it proper, so that this will become zero only if P and Q are related in that relationship. So this this is not in the paper of the conference. This is detailed in another paper that we've published elsewhere in a journal. So the properties of these divergence, proper or improper, are to satisfy the reference duality, which means that you can actually switch the indices and then move from alpha to beta, being again exponent conjugate, and you keep the equality, and same for the proper divergence. And you can also, because it's not there's no symmetry, you can work on the symmetrization by using this simply this classical symmetrization principle. And the Hölder pseudo-divergence, the first definition, is actually projective because you have that property. In fact, these divergences have also some nice special case, because in fact they sort of generalize the Cauchy-Schwarz divergence with the parameters. So the Cauchy-Schwarz divergence is obtained by setting the parameters all equal to 2, and then you move on either with that improper divergence, which now becomes proper because it's equal to this one, and it's equal to the classical Cauchy-Schwarz divergence. And in fact, you can also prove that it, with gamma equal to 1, keeping the parameters that way, you can actually prove that it's the Bhattacharya, it becomes the Bhattacharya distance with this parameter 1 over alpha. So in summary, from the Hölder inequality, we could build two divergences which actually incrementally sort of specialize and include as special case already known divergences. So by playing with the parameter, we can actually move from one case to another just by playing with the parameters. Now, since we have divergences, we can compute centroids and actually do clustering. So the idea of a clustering is that you get density functions, and you will want to cluster them by finding some affectation. Each center, each density function being associated to one center, and minimizing this cost function, which is actually the symmetric divergence between every density function and its center. So that's the classical k-means objective. And for resolving this, we use the variational k-means, and we use the symmetrized proper divergence, which is this one, so that you don't have the tie of some kind of transitivity, which would not be, if it's not symmetric, would create problem in the optimization. So basically, I'm not detailing the algorithm more than this, but essentially it's the classical way of doing the assignment and recomputing the centroid. It's a classical k-mean. So basically you start from an initial set that you construct by randomly, sort of incrementally picking centers with minimum probability. And then once you do this, you can compute a centroid. So basically you can affect densities to their centroid, recompute the centroid of this affectation, and then loop until you've converged. This is the classical k-means algorithm. And in fact, we can test this on artificial generated data, and we've done this for two cases. So basically, we create a first set of density functions. One is based on a Gaussian function. So basically what is done is we center the densities from a global distribution having some parameters. So the parameters of the the mean of the distribution of the mean are there. And then from each mean, we create the variance based drawn from gamma distribution and with a covariance matrix which is just diagonal. And for each draw, we generate either 2 or 3 clusters, and in the result, I will compare with the sort of set the k to the exact, the sort of ground truth, assuming that we know the number of clusters that we generated. The multinomial is generated from the 9D simplex, so basically you have 9 sort of 9 indicator, and what you do, you pick a center from a universal form distribution, and then you generate a distribution by simply taking some softmax-like distribution over the simplex. And again, we generate 2 or 3 clusters that we ensure being balanced, and then we try to recluster to retrieve the configuration. And in fact, the result, which are more detailed, I mean, there's more result on the paper, show that actually we obtain the first conclusion somehow is to say that we obtain good results on 19%. And in fact, as a baseline, we use the Cauchy-Schwarz divergence as a special case, which is the classical way, one classical way of doing this. So when our parameters are all equal to 2, this boxed value is what you would obtain if you were using the Cauchy-Schwarz divergence. And in fact, we see that for this set of parameters, which is a generalization with the Hölder divergence, the results are better for the case k equal 2. And here for the multinomial, again, we outperform the Cauchy-Schwarz divergence with the distribution of parameters is a bit less clear in terms of the performance, but still we keep a good performance and a stable performance compared to this Cauchy-Schwarz divergence. We also note that whenever we see in the result that whenever the task is more complex, meaning that we increase k, keeping the ground truth value as being the correct one, the performance decreases because the complexity of the task, of course, increases. So basically, in conclusion, I presented a generic principle for creating divergence function from inequality. So as soon as an inequality can be proven, the tightness of that inequality induces a divergence. The Hölder inequality is one case where it can induce proper and pseudo divergence. And in fact, including the interesting case of the Hölder divergence is that it includes as special case some already known divergence over which it shows to have better performance for clustering and basically a density distance measurement. Thank you very much. Yes.
Very good work. So my question is that for these divergence functions, so the Riemannian metric they generate, and also the Riemannian metric they generate. What does that depend on your parameters?
So the Riemannian metric.
Yes. Generate by your divergence.
So what do you mean? Does it depend on your?
Because you have these parameters, you have the alpha, beta, gamma.
The divergence will change depending on. So the Riemannian metric will also change.
Will or will not?
Will change because
Because the alpha divergence it will not change. So this is the part where the alpha divergence and maybe some other generalizations that are good in the sense they generate the same Riemannian metric.
True.
And a family of the FIT metrics. So there will be one family of FIT.
No, but yeah, I believe it will change.
We have to try to
Yeah.
may not change.
Okay. Yeah.
I bet it may not.
Yeah, I think it may not, but we have to check.
Okay. Yes, thanks for the question.
Just a very quick one. If you get
So the Kale divergence. So you're talking about the Kale divergence. It arises from from the principle of so the inequality that generates the Kale divergence is it also arises from an inequality. I've read that somewhere. Do you know, Frank? The Kale divergence, which inequality it arises from?
Maybe it's the definition of cross entropy and
Jensen equality. Jensen equality.
Yeah, it's a Jensen. Yeah, exactly. Yeah.
Time for another question?